Sasha, we're okay?
Yeah, we can start.
Thank you. Thanks for coming. So in the last lecture, we considered a remarkably simple example so x was a square. G was the dihedral group acting linearly on the square. On R2 and stabilizing the square. And we discussed the fundamental picture, the quotient x to x modulo that's all we discussed. Actually, I always draw x upstairs and g x modulo g downstairs. And this mapping is always called pi in my case. It's the orbit space mapping. And what we observed is upstairs is a square, and downstairs is what I call a wedge. And the reason we could identify this with a wedge is because we found a fundamental region up here which helped us identify this. It's called fundamental region. And it's identified with a quotient. And the easy example that you keep in mind is the example of fractions. You have all of these ordered pairs, where the bottom number is not zero, that's upstairs, and downstairs is the equivalence class. And we take in each fraction, in each equivalence class, a special element, so that the denominator and numerator are relatively prime. Here, we have upstairs a picture here, which is defined by inequalities So such a wedge, such a square is defined by inequalities. So x is defined by inequalities and equalities. I'm just saying the two operations, equalities and inequalities, are fundamental for this picture, defining these structures. And downstairs, same. You start upstairs and you found a fundamental region to understand downstairs, but downstairs also defined by inequalities and equalities of an algebraic nature. I hope you understand what I mean. You understand what I mean when I say algebraic. I mean an algebraic operation. It means something like, here I'll give you an example, x squared plus y squared less than 1. Okay. There's several points when you look at, I hope you understand this point. You have this thing, and this is what it's defining. And you notice that the coefficients here are all in a very small number field. You notice that the operations used to do this, x squared, y squared, and so on, all of these operations are defined over that small number field. You notice that we only have this inequality. Maybe we make it less or equal, so the boundary is in it. I'm not sure what we want to do up here. So the same thing we could do up here. So you get algebraic inequalities. Maybe you want to have something, also an equality, I don't know. But you don't want, something like sine of e to the pi x equals 17. That's an equation, sine of e to the pi x equals 17. That is a highly non-trivial, non-algebraic equation, right? And I have no idea how that looks. But if we restrict ourselves to algebraic inequalities, equalities, I think we have an idea how they work. So this is very good, and this is a wonderful theorem that in some general setting, you have an algebraic group action, this is even linear, you have an algebraic object, like a square, defined in an algebraic way. You make this invariant theoretic quotient, we call this invariant theoretic quotient. You go to the orbit space, pi, we've talked, it's Hausdorff and all this stuff, but the main thing, upstairs and downstairs have the same structure. You have to define a structure downstairs, but it's possible. That's a dream situation, right? It's really good. Upstairs and downstairs have the same structure. Well, I just wanted to mention that that is a nice theorem, that such a thing is possible. And I mentioned in the break, that theorem was proved first by applied mathematicians in the area of robots. Because this kind of problem appears in making robots, and they, of course, they're very good mathematicians also. But I have used this theorem on many occasions, where I can say something downstairs, knowing that I have basically algebraic operations. If you're interested, to be able to do this, this comes from, this is a corollary of basic results in real algebraic geometry. That's a subject of mathematics. It's a very beautiful and very important subject. Okay, that's just a little preview of important stuff. Let's return to yesterday's lecture. I want to reiterate that. It's Prabhupada mentioned this. You get involved when he was telling me when he first heard all these names in topology, like Hausdorff and all of these things, he got tired of it and quit. He was fed up with it, right? I mean, he just couldn't stand it. But it's useful terminology, I think. It just gets on your nerves. So let me just put it. We have upstairs is a topological space. So that's okay, right? Everybody here, as we say nowadays, is cool with the word topological space. It means, as you pointed out, we know what open sets are. And therefore we know what closed sets are. Right? I mean, so that's about all there is to it. And we know what continuity means. Yeah? Just let's recall here the key fact is X and Y topological spaces, whatever that means. You know what open sets are. Recall that if they're topological spaces and F is a map between them, it is continuous. We need to know what it means, continuous map. And that's the wonderful thing about the way this thing is defined. If and only if F inverse of an open set is open for all U open in Y. Pre-image of open set is open. That is the right definition. It took a while for mathematicians to make that definition. but after we understood this is the right definition, of course. And for metric spaces, this is the same. So I should make a remark, since you haven't had too much experience with metric spaces, with this topology. If X D is a metric space, sometimes I call D a distance function, or a metric space, then continuity, then the open sets are the arbitrary unions of metric balls. So just keep in mind it pictures some terrible open set. For example, on the plane, that's an open set, U. That's the way an open set might be. And to show that it's open, what you have to do is around every point, x1, you can find a ball in there. Oh, what is a ball? A ball, so a ball of radius, say, r, around the point x is the set of points y such that the distance from y to x is less than r. Right, that's a ball. So here you might have a ball of a certain radius. You can't be too big or you go outside. So you need to be able to pave this thing out with balls. Right? You need to be able to cover it with balls. Maybe it's very delicate if you need to get in. If you really need to do this in applied mathematics, it's a very delicate thing with these special balls and so on. If you need to work with in applied mathematics, it's very hard if the boundary is very difficult. But you need to cover this thing with balls, right? An open set is just a union of balls. And now I call it a ball, but I hope you know in dimension 3 it looks like a ball. We don't have, basketball. So a golf ball. I used to play golf. So that's what it looks like in dimension 3, but this is arbitrary dimension, some ball. That in the metric space. Or infinite dimensions. The metric is maybe in a function space. So who cares? So that's what the topology is in that case. Topological space, and we know what continuity means. And so what you need to keep in mind is the goal of this thing is, when you have a group action, is you have X, you have a G action on X is topological. Let me start making a list here. X is a topological space. That's the first thing. G acts by homeomorphisms. So this G acts by homomorphisms. It's action by they're homeomorphisms. That means they're bijective, contiguous both ways. Action by homeomorphisms. Preserve the structure. Topological space, preserve the structure. You make a quotient. You go to X modulo G, just like we did here. Here we had a fine quotient. I mean, we saw this as a wedge because we found all this stuff. But maybe in general we don't want to have such a fine quotient. So the best you want to do, this is in the lingo nowadays, you're allowed. So my granddaughter is 18 years old, so she's about a little bit you're older than 18, but more or less the same. So she would call this a cool topological space. And if you have a cool topology, whatever that means, then downstairs you want to have the same type of thing, to have a cool topology downstairs. Whatever that means. Even my 18-year-old granddaughter would know this. And if you have this map from one space to another, both have this cool topology, you want this thing to be continuous. Wouldn't you? Yeah? Wouldn't you? And I said over here, if you have some guy up here like a square, which is defined by algebraic inequalities and equality, that would be sort of a cool space, and you want the same type of conditions downstairs, algebraic inequalities, equalities, and so on. We want to be able to introduce that kind of structure downstairs so that this is structure preserving, this idea of structure preserving. So structure preserving is what this thing is doing here. Preserves the structure, and I've used the silly word cool to emphasize it doesn't matter what that means. It matters that you should preserve the structure. If upstairs is cool, then downstairs should also be cool. And this morning also already mentioned by Mr. Weiss, if upstairs is Hausdorff, you mentioned Hausdorff as a condition, you would certainly hope that downstairs is Haus. Or if upstairs is something, then you would hope that it's downstairs. So there are various properties. My favorite property, a very nice topology, so I exchanged the word cool for nice, just to have some fun. A nice topology has the property that you can separate. This is like Hausdorff's. Hausdorff says you can separate points with open sets. You can separate closed sets with open sets, disjoint closed sets. Closed sets with continuous function. This is jargon, so that you can keep it in your head. With this jargon, you can keep it in your head. But nice topology means you can separate closed sets by continuous functions. I'm going to make it precise, of course, which I did yesterday. It means in a picture, here's one closed set. By the way, quite often in topology, measure theory, and so on, you will see closed sets and nice sets, for example, denoted by F. And the reason is the French word for F starts with, for closed starts with S, fermé. Yeah, so the French, I'm sure somebody speaks French here, so you know, what is it Romanian for closed?
Închis.
Huh?
Închis.
What's she saying? I can't even.
Închis.
It's not fermé.
No.
It's, anybody speaks Spanish? Yeah, somebody speaks Spanish here. What is it in Spanish for closed?
Cerrado.
Ah, it's different in all of them. Abgeschlossen auf Deutsch. Anyway, when you see F in the literature, for some reason or another, maybe Bourbaki, many times the closed sets are denoted with F. Okay, so you have closed set F. I'll call this just for fun F0. And another closed set, they're disjoint, F1. So F1 and F0 are closed. So F0, F1 closed in X. You should always draw a picture, and then I like Greta Thunberg so much. I have to always draw a green picture. So we draw a green picture here. You certainly would like to separate closed subsets by open subsets. What would be a goal is this picture. Let's call this thing U0, and let's call this thing U1, open. U is always open for me. I don't know why. U is, U and V and so on is always open for me. Maybe Martin, maybe it's because of Urizo. So U is, I don't know why I have it. Anyway, one nice condition, nice topology would be given, let's write here, given F0 and F1 closed, there exists, there exists open sets U0 and U1, which contain F0 and F1 respectively. By the way, when you write in English, probably you should write a comma before respectively. That's always a question, I think, so that, or with U0, UI containing FI, and U0 intersect U1 empty. So you reproduce this picture. So you can separate, you have two closed sets. You can put open sets around them, which separate. Now Mark knows that he looked at topology books when he was in Kenya. What's that called? Is that called T3?
T4.
That's called T4. Okay? So these are the trend, that's a variance T4. Then there's another one. While I'm on this subject, when there's another one, if you have, but T4, now Mark, it's great that he's here, T4 for points, so I never know if P0 and P1 are in X, then there exists open sets, U0 and U1, same business with P0, PI and UI, and UI intersect, U0 intersect U1 empty. And that picture, of course, here's P0 and P1. And let's have our ecological cover here, green. These are the open sets. What's that one?
That's Hausdorff.
That's Hausdorff. Okay. So usually we require in geometry, classical geometry, what we're talking about in this course, we usually require at least Hausdorff. And this, of course, this is Hausdorff. And what's the Trennung's axiom? It's high or high?
One.
One.
One, I think it is two, right? It's T2.
Huh?
I think it is T2. Let's see.
Yeah, I think it may be T2. What is the axiom that points are closed?
T1, I think points singleton circular is T1.
So a point.
That's
Yeah.
equivalent to Hausdorff, so let's see. No, it is not.
So you think this is
It's T2 in this
this is T? I don't know what.
It's T2. Oh, sorry, T2. Yes.
I think it's T2, but I don't remember very well. T for Trennung, and Trennung, it means separation, and you can see why it's separation, because you're separating sets with open sets. Yeah. So that's some of the stuff. Yeah, but here I think here's a useful axiom that I use all the time, and I never know what number it has. Maybe T4 is in the setting of T4. So F0 and F1. There exists a continuous function F on X, real value, such that F restricted to the one set is identically 0, and F restricted to the other set is identical to 1. I use this a lot. Now, what is that, Prabhat, in your mind? Is that you mentioned that's using horizontal lemma, that's the same as T4.
I think that's T5.
It may be T5,
That's completely normal.
but you can prove that this holds in T4. Yeah, I think it's equivalent. It's very close, and I'm almost sure it's equivalent. That's what Marty was saying. Is the equivalence is what is called Urizone's lemma, and it's really, to me, this is a very strong thing, because you see, what you do is this. Once you have that function, that I'm talking about here, here's F0 and here's F1. So you take small epsilon, of course, and here you define this to be where the function is less than epsilon, and here you define this to be where the function is bigger than 1 minus epsilon, or epsilon small, right? And so, of course, then you have this beautiful picture. So these are the good properties that were given to us by Hausdorff, or Tikhonov, but I believe really Hausdorff, to make many things precise. And I would like to note the following lemma. So the setting I would like to consider is a more general setting, which we're going to discuss in a minute, but even I'm going to discuss this in a really general setting. So X is a topological space. These guys have looked at books, I'm sure you're right, let's say, which is, for example, T4. So a reasonable topological space. It could be Hausdorff, we could make the same discussion, but T4. That's the setting I'd like to, that's a reasonable setting. You can separate closed sets by functions, right? And, okay, and G, this is a G action. By homeomorphisms. So continuous mappings, whose inverses are continuous. That's a reasonable situation to set up, right? And with quotient, x by down to this quotient pi x modulo g. Reasonable setup, right? Reasonable topological space upstairs. Here we had much better. We had a square which is defined by inequalities. Here just a topological space upstairs. A group action that preserves the topology. Let me emphasize here, this means a group action which preserves the topology. I'm writing it another way, just so you keep this in mind. Action which preserves the structure. Right? And your dream situation is then the quotient topology, whatever that is, that's quotient topology. This is the natural topology on the quotient. I'm going to talk about it. The natural structure on that quotient is the inequalities and so on. The quotient topology is also T4. That's, you know, when you're sitting there and you're getting hit with the abstract stuff, you should at least say, this is good. Whatever T4 is good. Well, I went over here, I exaggerated it. If you have a cool topology upstairs, you have a cool topology downstairs. Now, all I did here was go like this. Yeah? So this would be a situation like this, and of course this is wrong. And so, this is wrong in general. I will make some examples. This would be the dream. Right? If it's cool upstairs, it's cool downstairs. If you have some reasonable separation possibility upstairs, then you've got it downstairs. If it's real algebraic upstairs, it should be real algebraic downstairs. If it's complex algebraic upstairs, it should be complex algebraic downstairs. If it's complex analytic upstairs, it should be complex analytic downstairs. Right? If it's T4 upstairs, it should be T4 downstairs. Or maybe you lose a little bit. If it's T4 upstairs, maybe it's T3.5 downstairs. I mean, after all, you're doing something here. Maybe you're going to lose a little bit. Yeah. So this is somehow a dream. And that is sort of introduction to my lecture today. I would like to discuss this dream and in which situation this dream should be true, and to motivate more general settings that I'm going to talk about in the course. So the goal of the lecture today is the goal of the lecture today, this afternoon, is to one, goals. So goals. One, show that this is delicate, show by examples that this is not at all true in general. And two, show that it is true. It is true. By the way, I use the word true. True is a very much of a loaded word. I don't even know what true means. Right? You know what I mean? You don't like what I'm saying, Tristan? Do you know what the word true means? I don't know what it means. In your mother languages, think about the word true. It's very delicate. It's not so. What I like, what I think is, and we see this in German, and I'll tell the German expression here, that holds in the case of G, a finite group. Right? This statement holds. You know that expression, I think it's standard in many of our languages. Right? It holds. Yes, auf Deutsch is give. Yes. It's maybe, you can see in gelten in German, it is valid. I mean, valid is sort of it is valid in many situations, right? It's too much. But we say nowadays it holds but to say something is true is sort of, hey, that's true, that's false. I don't know. Okay. Okay, so the finite group. And this will motivate, in case you're interested where I'm going in the next steps, the study of a very important finite group. Finite group. Not just the dihedral group on the square and so on, namely the permutation group of any set S. S is dangerous of any set X. Well, which is fine. With X, finite. Permutation. You understand what I'm saying? A set of permutations of a finite group, of a finite set. That's sort of an important finite group, yeah.
And what topology do you have the finite group? Just
That's one of the advantages. You don't care very much. I think that's a very good question. I don't know what he was thinking about actually, but I'll tell you what I think you mean. Okay. What Abik said, his question was, what? So Abik question. A question Abik. What topology on a finite group right? I mean, it's
finite set because.
or a finite set. Oh, okay, a finite group set anyway. Right? All of this. Right? In some sense, what he's saying here, if I'm going to apply this to a finite set and so on, there's not going to be much of a topological question, right? But what Abik immediately had in his mind is this picture. Yes? If G is finite and X is finite, there's not much to say here about topology, right? Any set is open if you like, if you want. All sets are open. But what he has in mind is, in general, if G is something else, like the affine group, or X is the plane, or various other things that we've been talking about in this course, this mapping had better been reasonable. So it had better be, the action mapping should itself be a reasonable map, right? So this is, what topology, this should be continuous, at least continuous. Depending on the setting, maybe real algebraic, maybe complex algebraic, maybe analytic, at least continuous. Whatever setting you're dealing with. Yeah, that's what you maybe had in mind. But with everything inside here, finite, it's a joke, right? I mean, you don't have to worry too much about it. But you will see very soon, if even studying the permutation group, we come to a situation like this. Okay, so I want to do one example where, well, no, first of all, I want to recall the quotient topology. So you have a map from X to Y, and you want to say, let's call it F, say that and define the sets U on Y to be open if and only if pi inverse, F inverse of U is open. Topology is a matter of open sets. Yeah. All I'm saying is if downstairs I give Mr. Pham an open set, or he gives me an open set because he doesn't have much experience yet. You give me an open set, you give me a set and you claim it's open. I just have to check. I take its pre-image. Is that going to be open or not? Yes. That's not so hard. And what that forces is, that's the biggest topology. I use the word big. Most open sets you can have. I never know. You people who have looked at this subject, it's finest topology. It's called finest because you have the most open sets. Rough, you don't have much, right? Isn't that right? So there's these two words in this subject, rough and fine. And I don't even know how to translate it. Huh?
Depends upon the author.
Is that right?
Yeah.
Okay, but I don't know, it's very hard to translate those words in German, for example. I would not know, here's some German-speaking people. Rough, the translation, in case you want to know what I would say rough is grob. And to talk about a topology being grob, I can't, it doesn't make sense to me, but it does it to you? Not really, right? Eine grobe just so I don't know. There's some translation. I don't care. So, so I wrote it down. A set's open if and only if its preimage is open. Right? And here, that's in the group setting. In the setting. A G action. G actions. So we take pi inverse of u is v. I call this, let me call this v. Should be, so pi, that's notation. So u, we'll say u is open downstairs. If and only if v is open upstairs, open, and of course, this is the quotient, x goes to x modulo g, so a preimage of any set down here, u, preimage is v, this is clearly G invariant, because this is if you take a point down here, its preimage is the orbit of some point upstairs. So this is the orbit space. So this is automatically G invariant. So you can check very easily, U is open downstairs if and only if the preimage V is open upstairs, open and G invariant upstairs. Okay, this is a very nice criteria. We talked about this with some other students recently. We talked about this before. So this is more or less completely clear. You can separate orbits by G invariant open sets. So this is a beautiful condition. Open downstairs, and the quotient topology means you pull it back and look what it is. It has to be open because it's open in the quotient topology, but of course it has to be G invariant because that's the case. That means that U is simply V modulo G. So you take sets downstairs, you lift upstairs, they're G invariant. I mean, the quotient of V upstairs, modulo G, is what it is. So this is a very simple thing to consider, at least conceptually. And it's not so simple. My favorite example, which some of you know, a dangerous example. If an example can be dangerous, I just say that as a provocation, of course, where the example is the quotient topology is not even Hausdorff. I have not proved that, but I mean it's an easy exercise, and it's indicated by the notation that I would love T4, but Hausdorff is even weaker. Where did Hausdorff go? Oh, here it is. Did we decide this was T1 or T2? This is T2. Anyway, it's Hausdorff. You can separate points, not open set, is Hausdorff. And the example is not even Hausdorff. It's very easy by notation that T4 implies T2. The bigger the numbers, the stronger the conditions in these Trennung-Axiom. So it's not even algebra. Let's do this example together. It's an easy example. Some of you know it, so you're going to be bored. Okay, ready? Here we go. So the group is, let's say, I don't know, R plus with multiplication. I think that's good enough. You agree that's a group? Right? I mean, right? Take a positive number, how do you get the inverse of it? 1 over it. What's the group operation? Just multiplying the two numbers together, right? That's certainly a group. Okay. And to take this action on R2, and I'm going to make something a little bit optimistic, -0. I'm going to pull out a point that looks horrible from the point of view here. It's a fixed point of this action. I'm going to tell you what it is. The action is, so an element here is, I'm going to call it lambda for some positive number. So lambda of xy is lambda x, lambda inverse of y. Okay. That's the simplest example that I know that's bad. Okay? Okay, everybody here, I know this is, for various people here, this is a new thing. So let's have fun with the simplest example we can think of. Okay. Okay. So I'm going to draw the picture. Here's the xy axis. And I took out 0. So that's not there. I'll write this as x-axis. This is a y-axis. Tell your engineering friends. And now you start doing what we did with the square. So this morning with the square, we looked at various points and tried to understand the orbits. So let's take a point here. This point has, well, I'll just write it in general. That is the point 0, x. No, 0, y. Any y. That's very bad because y looks like a variable here. Let's make this 0b, any point b. Okay? Okay, what's the orbit of that point? So somebody come here and write the orbit down here. That's easy. Crystal, you got to come here. I'm going to make you write down it all. Right? What is the orbit of this point? 0b. Right. You know, late in the afternoon, everybody should participate, get some exercise. What is it? You gotta just write it down. Very good, very good, very good. Very good. Yay! Great, wonderful, thank you. So that's her version of lambda. I'm going to write it. Okay, that's more easily to understand. She wrote lambda, but you know, Crystal, when you write here, it makes sense to be careful. So that's ordered pair 0 lambda b. Yeah. So you should have written it. I mean, I'm not being exaggeratingly formal, but it helps, right? And she meant to say for lambda a positive real number. Yeah. Abek doesn't look happy. What is going on here?
Lambda is fine by definition.
Huh?
By definition, lambda satisfies that.
What satisfies that?
Because the action of the group is.
Oh, that's lambda inverse I wrote here. Is that what you're worried about? What are you worried about, Abby? If he's worried, that means other people are worried.
Oh, I'm just saying that extra condition is redundant.
So, no, let's make sure everybody's on the same page. So you take, it says here, you take a pair of numbers and you let a positive number act on it, and the action is you multiply the first thing by lambda and the second thing by lambda inverse. Okay, if you take the point G0b, you have to see where you go. You multiply the first point by lambda and you get 0. And the second point by lambda inverse. But lambda, if I'm just looking at the whole set, I don't care whether it's lambda inverse or lambda. Maybe that's what you're talking about. Yeah, that's what I thought. So if she did it in her head too, the same thing, I could write lambda inverse. But it doesn't matter because 1 over lambda and lambda I get, right? So in any way, so with Crystal's contribution here, we get this entire thing here. Yeah, okay. Well. Now, it's just a terrible thing, but in many traditions, and I tell this, it's a terrible thing because nowadays we are really supporting women in mathematics, for example, and it's so important. It doesn't matter if somebody's a woman or a man, it doesn't matter. But in the old days, when you have a baby in some countries, if it's a boy, maybe you know, if it's a boy or it's a girl, you hang a flag out that's pink. Do you know that in some of your cultures? You know, you hang out a flag or something that is pink. And if it's a boy, you hang out a flag that's blue. Yeah. And that's the reason I gave Crystal the pink. You don't mind. No. And now, if somebody else would come up here, this orbit would be that, right? Right? Yeah, that would be the orbit there. You agree, Crystal? It's the same thing. Okay. And then Greta Thunberg's orbit is in this case generic. And in some sense, actually, Oppic is a little bit right about this. Because, let me just put it here for fun. If we put here the point A0, and the general, that's that point, and somehow it goes to lambda A0, and here, what he was talking about, this goes to, this is what Crystal was talking about there, this goes to 0 lambda inverse B. Alright? It's a little bit like the orientation. As lambda goes to infinity, let's think about lambda going to infinity. Big and small, you should think about it, right? Lambda goes to infinity. So as lambda goes to infinity, this thing goes to 0. And here, as lambda goes to infinity, this thing goes to infinity. And so your feeling is that this thing comes down here. This is the simplest so-called dynamical system you will ever see. This is trivial. Yeah? It looks like that. And so if the generic orbit, which I dedicate to Greta Thunberg, is a point here, it really somehow follows this in an orientated way. It looks like that. It's a hyperbola. Right? And then if you have something here, then downstairs, what Crystal wrote for upstairs is okay, the same thing. I mean, it's not very, and let's see, I think the same thing over here. I mean, it goes like that. So then we have all the Greta Thunberg orbits. They go, and maybe, how's that go? Okay. That's the standard picture of most trivial dynamical system you will ever see. Right? Anybody in applied science would laugh at us for considering that. It's so trivial. Okay? Okay? Good. Now let's look at the quotient topology. Okay. Notice the group is R plus where did it go? Where's the width? Oh, I didn't know that. The group is R plus. And R plus is highly non-finite. And the key is, you will see, and that's what I'm motivating here today, is it's highly non-compact. So it's just non-compact, there's no such thing. So it's not finite. So it doesn't violate what I was saying over there. And in fact, it's not even compact. It is not compact. And the word compact here is fundamental. So we will talk about that later. And now we look at the quotient topology. This is just the word compact. Let's look at the quotient topology. And it's interesting. So, quotient topology, let me write the orbits. Quotient topology, the orbit space. Orbit space. X modulo G. Okay. And now, just for fun, I'm going to put color, this is color coded. This is exciting. It's like modern graphics, computer graphics. I'm going to put the equivalence class, let me put the equivalent, oh yeah, why not? Let me put the equivalence class here of the blue boy, A0. The equivalence class of A0 is here. The blue ones, I'm going to do the blue ones. That's the orbit of A0. And now the equivalence class of 0b. Okay, that's B orbit. So the equivalence class is 0b. 0b. Okay? Okay? Okay. Now, what did I say? The open neighborhoods of this equivalence class correspond to invariant open sets upstairs. So, invariant open sets upstairs is the usual topology on R2. So let's be a little bit optimistic here. Here's A0, and it's certainly the open set that contains A0 has to contain A0. So if it's an open set here around A0, it has to contain something like a disk like that. So I look at an invariant open set about A0. That's what the quotient topology is about. Open set around A0. About or around containing A0. Okay, so it has to contain a little ball here. That's what topology is all about, a little ball. And who can come up here and have fun? I know that Nicholas knows this, likes this example very much. What's the open set that contains that ball that's invariant?
I mean, it's the whole right hand side.
Okay, come dry. We'll make you go.
Maybe.
Make you work. Come on. What color do you like? We have to have a decent color for that. Oh, why not blue? Just to correspond, because it's a neighborhood of the blue point.
Yeah, okay.
Okay.
I mean, in fact, because we said it needs to be invariant,
Right.
don't we then need the whole blue line?
Well, you need the whole real line.
So we need
The whole orbit is in.
yeah, so the whole orbit, so actually it goes all the way here. So it needs to be some open set around the whole, well, let's say at least the real line. And that,
It has to be invariant.
Yeah, exactly. It needs to be invariant, so it needs to be open neighborhood of that line, and therefore automatically it will also intersect with any of the other orbits on the right hand side of the plane.
Yeah.
So basically, it looks at least something like this. So basically contains everything here on this.
No, it won't contain, I mean, come on, we start with this little open neighborhood C and push it.
Yeah, and then you extend it. So you have an open neighborhood around the line,
Yeah,
about the positive x-axis,
yeah.
and therefore this will intersect with every orbit which is either in the upper right side or the lower right side.
I want to make a G invariant result,
Exactly, so every point which intersects,
which goes into this little disk.
yeah, of that we need to include the orbit as well.
Right. So don't conclude there's something up there, nothing goes into this.
But isn't it then, I mean, it also needs to be an open neighborhood about the whole orbit.
Yes, I agree with what you just said, it has,
Okay, so every open neighborhood around the x-axis will intersect with every orbit which is right side.
I disagree completely. If you take this little disk here and you push it with the orbits,
Yes.
it doesn't intersect the orbits up here.
Oh, I see.
You see what he's saying? You agree, it has to, all the orbits that go in here, it has,
Yeah.
you see what he got mixed up, but you agree, it doesn't intersect the ones up here.
Yeah, okay.
Okay, so you get basically this, right? Okay, great, we agree. You see what he's doing? Yeah? Yes.
Why do the orbits act like that?
Why do you get what?
Why do the orbits act like that? So why do they have this shape? Because, okay, say you have a point here, right?
Okay, yeah, why do she's asking why is the orbits like that? And if you see that every orbit is a hyperbola because it's lambda inverse, and you can just write down the equation for that orbit. Okay.
But then what is the action of the group?
So if x and y are not zero,
Yeah.
and you have the set of points lambda x, comma, lambda inverse y. I mean, she's asking a very reasonable question, why do the orbits look like that? Right? Yeah? So she asked why it should be. So the set of points will be like lambda x, lambda inverse y, yeah? 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 And now it's a set of points, S, say the coordinates are ST. So it's the set of points ST such that S times T equals lambda equals X times Y. You see, I wrote down the equation for you. Yeah. I know this example so well, I don't even have to write down the equation. But, right, the orbit, that's the set of points in the orbit, and say if the coordinates are ST, it's a set of ST so that ST, product. So you kill these, by multiplying you kill that. And so ST equals X times Y. And X times Y is some number. So that's a parabola, S times T equals some number. Right? That's the equation of a parabola. Right? And so Nicholas was worried about ours up here, but if you're only considering open sets down here, you're never going to get into these open sets down there. But if you saturate these, we call this a saturation, you start here and you saturate this open set, you're going to get all the parabolas that go in there like that, right? You're going to, as he said, you get the orbit. But anytime you get away from the orbit, you're going to get the parabola that goes up here. So it's going to be like that, right? Okay? So that is, no matter what you do, the invariant open neighborhood about A0 is going to look like that. Okay? And now no matter what you do, the invariant open neighborhood about this point is going to look the same. So we take a little ball. So I don't know, here's the point AB here, 0B is here. and we take that little ball, and we push it, and we get it, make it saturated. We take all the orbits that go in there. That's great. This side it looks like this. Yeah? But this side, look out. Look out. You see what happens? You see what happens? You take any invariant open neighborhood here and any invariant open neighborhood here, they intersect. Yeah? They intersect. You see them intersecting here. Okay? So that says, what that says is, you people who wanted Hausdorff, what you want in Hausdorff, you would like to have an open set here and an open set here, and they don't intersect, and that would be wonderful. But in our case here, you have an open neighborhood here, and you have an open neighborhood here, and you have an open neighborhood here. Well, it goes on there, and this goes on there, but it intersects in a huge set. You should think about it. It's a very interesting example. It's very simple, right? It's an example of the simplest possible example that anybody could write down of the action of a group which is far away from finite. It's non-compact, right? It's the simplest non-compact thing you can think of. Positive real numbers, yeah? And the quotient topology is not Hausdorff. It's not Hausdorff, therefore it is not T4. Okay? That's a wonderful example. So, good. Now, that's an example. Where to go? Here we go. However, by finite groups, there's no problem. And I'm going to show you the most important method at the first of the study of finite groups. The method is called averaging. And the method comes from probability theory originally, and I will explain it in probabilistic terms. So, what I'm going to show you is so the theorem, the proposition is not a hard theorem to prove. If X is, say, T2, Hausdorff, or T4, or whatever you want, then, and X modulo G is equipped with the quotient topology, this is the right topology to put on it. Then X modulo G is T2 or T4 or whatever you want. Comma, provided G is fine. Well, whenever, if G is fine. I said it in words, but I didn't write it. It's not wrong. So it's false in the non-finite case, there's the first example, and it's true in the finite case. Okay? And the method for proving this is more important than the statement. The statement is trivial, but the method is very important because you see it everywhere in life. The method is of proving this. The method of averaging over the group. And this method of averaging over the group comes from probability in statistics. So I want you to, I want you to learn this method. It's a fundamental method. Okay. So let's look at a finite probability space. And let's take a stupid example, a pair of dice. I spell dice, you spell dice, D-I-C-E?
Yeah,
Pair of dice? Pair of dice, yeah, that looks good.
yeah.
Guy from Uzbekistan telling an American how to spell dice. Now, a pair of dice. Now you tell me, let's see, here we go. Do you all remember the dice? There's 6 possibilities on each side, right? So there's 6 possibilities. And here's the outcome of rolling a dice. It's called outcome in English. You roll dice. The result, it's called outcome, is you add up the 2 numbers. Right? And so the numbers go from 1, 2, 3, 4, 5, 6. And here the possible outcome is 2. And there's only one way that happens, right? You get both. Okay, then the next possibility is 3. And there are 2 ways that happens, right? 1, 2, 2, 1. 2 ways that happens. The number 4 could come up. Oh my goodness. So 3, 1, 1, 3. Oh, it's very easy. It just doubles, right? 3, 1, 1, 3.
2, 2.
Oh, 2, 2. That's it, right? Oh, does it go like this? 3, 5 could come up. 4, 1, 3, 2. That's it, right? 4, 1, 1, 4, 2, 3, 2, 2, 3. It's 4, right? Does it just increase like that? Am I making a mistake? I don't want to. I never play for money. So, and here we go. The 6 can come up. 4, 2, 3, 3, 3, 5, 1, 1, 5. Oh, it's 5 of them. Right? 7, is this always go like this?
Sorry, can I add something?
Huh?
For the first one, for the 2, I would think that we also have 2 probabilities. Is that correct?
I haven't said anything about probabilities yet.
No, like
Results.
two ways to get 2, right? Like
2 ways to get 2?
yeah.
No, 1 way. Both dice have to be 1.
But then, if like for 3 we have 2 cases like 1, 2, and 2, 1, then we're like differentiating between the 2 dices, right?
Yeah, there are 2 ways to get 3.
Then for 1, if we are like making a difference, for 2, sorry, if we're making a difference between the two dice, that we have like one and the other one.
Yeah, of course, they're two different dices.
Yeah, so,
It's just one of them.
Both have to come up, if you're gonna get two, both have to come up one. Come on.
The other one is also pretty-
7. I'm getting tired of this, but let's finish it. 7, 4, 3, 3, 4, 2, 5, 5, 1, 6, 1, 6. That looks like it's going up. Does it continue? Well, 12 is up here someplace. There's only one way to get 12.
Then it's symmetric, I think. 6 and then 5, 4, 3.
Does it go? I hope it goes down like that. Is that right? Oh, you people know better than I. You see, I couldn't care less. So, 5, 4, 3, 2, 1. Okay? Okay. You agree? How many possibilities are there altogether? So the probability space so the probability space X equals, consists of the numbers 1 through 12, right? Right? That's the probability. And the probability of a number is the probability is equal to the probability of the die D equals the result, call it R, equals I.
Because
You disagree with something I've written?
yeah, one shouldn't be an X, should it?
This, you're too quiet, I can't hear you.
One shouldn't be an X, should it? Because you can't roll with 0.
Oh, it should be, yeah, 2.
You can't roll it one.
2.
2 dice.
2. You're right, I don't know how to make 1.
One
Well,
dice.
Frederick told me, my grandson, 1 plus 1, 1.
Well, one dice is falling under the table.
Yeah, oh, that's the way it is, yeah. Very good, he's like, okay, 2 is, you have to start with 2, right? Very good. Okay. So we have the numbers 2 to 12. Here's 2, 3, 4, 5, all the way up to 12. I'm getting tired of this. And now you make a graph, which is probabilities, abilities. And the probability you get a 2 is, wait a minute. Oh, now wait a minute. We have to figure out, the probability you get a 2, there's only one way to get a 2. And there, how many possibilities altogether are there, do you know?
36.
You know, it's 36. Oh, that's almost completely clear, because 6 times 6 is 36. So it would be 236. 236.
1. I think it's 1. Can we say it's only one way?
Oh, there's only one way. We had this big discussion with this guy, and he confused the daylights out of me. There's only one way, 136. And the next one, to get a feeling on it, it's 236, so twice as high. And the next one is 336. So it's going up linearly, all right? Oh, it's great. We can do it. It goes up linearly. That's what you're telling me. It goes up linearly. And where does it top out? At 7?
yes.
Huh?
Yeah.
I mean, it's 6? 6 it tops out.
No, it's
7.
7's easier than 6? I think so. Oh, and the number is 6. So it tops out at 7, and the number is 636. Right? Right? And then it goes down. So if you made this continuous, it looks like this. Right? I knew you would have fun doing this. I see he's really happy about this. He was encouraging me to think that you could get 1 by throwing 1 die on the floor and you get 1. Okay? No, you could do it. It's very nice suggestion. Yeah? Now, you have to know what you expect to get when you do it. So this is called the expected value of this experiment. You learn all this stuff. Expected value of the experiment. Some people write E, but that's, I don't know. Expected value. value of this experiment. Okay? Well, it's the weighted average. Do you all agree? Do you agree? It's the weighted average. Is there any debate about that? It's the weighted average. 2 times the probability of getting 2. Plus 3 times the probability of getting 3. Plus 4 times the probability of getting 4. You agree, right? Right. Okay. This is called the expected value. So you average with weights. Okay? You average with weights. And now I'm going to talk to you a function about, talk to you about an idea in groups, which is averaging in some sense with weights. Fundamental technique in all of mathematics, which is as old as I mean really it goes back a very long time. Averaging with weights, where you're averaging over a group. Okay, ready? Go. Let X be a reasonable topological space. Reasonable topological space, I don't know what I need. Maybe T4, I don't know, T1, T2, Hauser, I don't care. Some reasonable topological space. And G action. G action. G action. Say continue. Okay. Let F be a function on X. The model for this function is the probability distribution. So the function here, you're happy because I have a graph. The function is to each number you associate its probability. Right? That's the function. Okay. Let F be a function, any function. And what we do, we consider the average function. I do not use the same notion as expected value. But it's really what I'm doing here is I'm averaging to get an expected value. You know it, it's a weighted average is all it is. Is the summation over, at X, is the summation of F of G of X over G and G. I'm averaging this function, in this case, times the probability of getting G. And in this case, the probability of getting G, I'm going to take the uniform probability. Please try to think with me. 1 over G. So, if you have X here, and you have, I don't care, X, it doesn't matter, and I have, here's X, here's G1 of X. Yeah, I don't know, some of them are the same, who knows, doesn't matter, all of them. And now you have the weighted average of this function over here. This is the uniform probability, it's the height 1 over G. It has the same probability for each thing. We call this the uniform probability distribution. It's the same. Auf Deutsch sagt man die Gleichverteilung. It's equal everywhere. Yeah? You have the uniform distribution. Okay? Do you get what I've written here? The average of f at a point x, you take f at all over the whole orbit of x and average it. What does it mean? You take the sum of it and divide by the probability of getting. Well, the probability of getting it is just we're using the uniform distribution. So the weight here is not so complicated as it is by distribution. Auf Deutsch die Gleichverteilung. Gleichverteilung. Yeah. Okay. And now, check it. Watch. Very slowly. The average of f at a point, let's say h of x, okay, I'm going to write very slowly here, is the same thing as summing over g and g of, what do I have there? F of g times h. I mean, it should be, this should be constant, right? So let's see here, times 1 over h, g. Okay. Now, let's see here, we have a really good idea. As g runs over there, I'm going to call this guy here g hat. Okay? You don't object. So as g is running, that's what is g? G is g hat what times h inverse? G times h is g hat, so g hat times h inverse. Yeah? Right. Well, as g goes through the whole group here, what happens to this thing? This is g. Well, that's the same thing. Yeah, that's the same thing as g hat runs over the whole group. Isn't it true? Isn't it true that as g hat runs through the group, this is the same thing as g hat h inverse runs through the group? Isn't it obvious or not? You understand what I'm saying? No. You get what I'm saying? Yeah? Here's no, it's clear, right? As g hat runs through, as g times, this is g. As g runs through the whole group, that means this thing runs through the whole group. That means, well, what is g hat? G hat is equal to g times h. So all I'm saying is as g runs through everything, so does g hat, g times h. It's completely clear, right? So check it. As g runs through the group, so does, what do I need? G times h, which is g hat. So I can just erase this here and say g hat, g. And I could call this G hat and G. And it's the same. So this, and this is the definition, it doesn't matter, it's A of F of X.
Sorry.
Yeah,
H could miss some of the points which I think.
you know, I have trouble hearing, so I'm gonna have to come back to you again.
Isn't the idea that this sum is supposed to be conjugacy class invariant, not invariant over the entire group?
No, what do you mean? I don't see any conjugacy. What?
We said what G, if as G runs through the group, G hat runs through the group.
Yes,
But you see, we're multiplying.
I'm just saying, let me formulate this in another way, okay?
Well, I kind of feel what might be the issue is that, I mean, you clearly have the inverse of H in there, therefore you get to the identity, and therefore, since you multiply by all other elements, you get to every element in the group. So you basically have every element.
Oh, no, I don't have, look, well, maybe you're right, yeah. As G, okay.
So you basically have the group times G inverse is.
Well, I don't see it, maybe I have to do something here with G inverse, but if,
Or AH inverse, whatever.
so if you don't believe me, if you don't believe me here, I take G, oh, that's what you're saying, Nicholas. To believe me, to make sure that I get everything GH, I take G equal to GH, H inverse. Right? That's the way to say it, right? G hat is this, and that's the process of G hat running over the group, and here, this is the process of G running over the group. It's the same. That's what you're probably asking, right? So just check it. Okay? So you can replace G by G hat. Okay? So that says that this average thing is an invariant function. This average thing is an invariant function. Now, why the devil did I this average thing is invariant? Let's write this, the A of F. So for all, let's write this carefully. For all F, any function you want, it follows that AF is G invariant. Check it. It's what we were saying here, going back and forth. You just check it. You put in H and check it. And I just checked it for you. For all F, any function you want, this is invariant. Now, let's understand why the professor had the sense to write the uniform probability here. I didn't really need to do that, did I? I could just add them up. I didn't use that. Let's look what happened. This is a really interesting technique. I think I first learned about this technique in Fourier analysis, but I can't remember. So I'll put it back up here so we can look at it. A of F, for any function F, the average, A doesn't mean Alan or somebody. A means average of function F, is defined at X, to average over the group using the uniform distribution, the function, and I scale it with the uniform distribution for some unknown reason. And it follows, so fact number one, I'm repeating what we just saw, this function AF is G invariant. This is a great way of making G invariant functions.
sense. You may not run through all elements of the group.
Sure. If G runs through all elements of the group, G times H runs through all the elements of the group. Check it.
The orbit of x and s of x would be the same. Or
I think what Deepak is giving you proof. He's saying that the action of G, look at the other way around. The action of G by left multiplication is free and transitive. That's what you're saying, right? You hit H with everything. It doesn't matter what H, you get everything. Right? Check it. This thing is G invariant. Then you ask a question, suppose F is already invariant. Again, that's an interesting question. Let's see what happens. A of F at X equals sum G and G of A of F at G of X. I weighted it with this probability distribution, but that's invariant, so I'm going to continue on here. Well, that thing's invariant, so that's equal to A, G and G. It doesn't change because it's invariant, so that's A of F of X times 1 over G. That's just a number. And that's the same thing as A of F. It comes out because it's not involving G. And this number comes out because it's not involved with the group G. And it's the sum over 1, over the number 1 of G and G. Right? I pulled out all numbers, yes?
Why do you introduce the average again within the sum?
Why would you do that?
No, why do you use the average in the sum again?
Oh, because I'm stupid. Sorry, it's terribly sorry. F, right? Really stupid, right? Well, it's Freudian, I will tell you what's happening, because it isn't. So, okay, you agree? So thank you so, right, this is the definition, right? And Mr. Weiss just told me I was stupid. You didn't say that, but it is true, particularly at this time of night. And, okay, so we averaged it, but it's already invariant. I said, suppose it's invariant. And so that doesn't matter. I mean, that means that's constant. So I pull it out of the sum. This is just a number I pull out of the sum. So I pull everything out of the sum. And I'm summing 1 over the group. What do you get when you sum 1 over the group? You get the number of elements in the group, right? So this is equal to F of X. Any questions? So if you take any function and average it, right, you get an invariant function. If you take an invariant function and average it, you get the same thing back. Okay? Now, this is a lecture for big boys and girls, not just for little boys and girls. So that says that the averaging thing is a map. You say? It's a map from functions, right? From functions, let's say that's the space of all functions on X. And you average a function, you get a function on X. And the notation of invariant functions is you put G up here. So these are the G invariant functions. So if you have a function, you average it, you get a G invariant function. Okay, that's a map. Check that this has good properties. The function, space of function is a vector space. This map better be linear. Otherwise, I've done something terrible. Averaging should be linear. Check it. It should be a good map in every sense of the word, right? Better be linear. Okay? Now you should make a picture. You should draw a picture. The whole space is here, the function space. A terrible, in general, maybe infinite dimensional space, I don't know. Function space. And you have a function f, and you have the invariant functions. Here are the invariant functions. And this mapping is a projection on the invariant functions. You start with an invariant function g. No, that's not true because that's in a group. That doesn't matter. I don't care. Big F, a big function. And you average this function. It's a projection onto the invariant functions. A projection means that it's a linear mapping onto the invariant functions. So, and not only is linear, but it maps onto the invariant functions, and the restriction to the invariant functions is the identity. Is the identity on the space. That's what a projection is. Is it not? You start with a point here, you don't move. You start with a point here, you move it down to the average function. This is a fundamental method. It is called averaging. It comes from probability, in my mind, because you're computing some form of expected value. Right? It's expected value over the group. You can always do this. It's a good technique in mathematics and physics that I know. If you average with respect to the uniform distribution, you get a projection from all functions onto the invariant functions. Okay? That's a wonderful technique that is used over and over and over and over again. The technique of averaging over the group. Okay. So, I'm very lucky I can give you the nice application, then we go eat. Okay, application. Suppose F1, F0 and F1 are disjoint closed sets in a G space X, so there's a G action on X, which is T4. Suppose further that they are G invariant. So disjoint, I'm going to put it in here. Disjoint G invariant closed set. Okay. The closed sets downstairs are the G invariants, the closed sets upstairs. Yeah.
What is it, G space?
G space is a space X equipped with a G action is all I mean. Yeah. He asked what is a G space, so I just mean. It's shorthand for you have a G action on this space, and if it's a topological space, I think it's always implicit that it's acting by homeomorphisms, that's all. Okay? G invariant closed sets. That means the complements are G invariant open sets. Right? Let f be a function on X such that f restricted to f0 is identically 0, and f restricted to f1 is identically 1. Let's suppose it's T4. I'm supposing it's a decent set. Remember, this is what we have. We have this two closed sets. Here's the two disjoint closed sets, and we have a function upstairs which is 0 and 1 here on these invariant closed sets. What about A of f? They're invariant. So what happens here if I take x in this point here, in this part here in f0, and I start pushing it with g? It stays there, right? Because it's invariant. I average it. It stays there. That means the answer you get is what? 0. You average 0 everywhere, you get 0. Right? So AF restricted to F0 is 0, and AF restricted to F1 is 1. Because if you have a point here, x, this is F1, this set is invariant, so all the orbits of every point in here stay in there, and I'm averaging the number 1. I'm just averaging the number 1 all the time. 1. It doesn't change. It's 1. Okay. I have obtained A of f is now a continuous function in the quotient topology on the quotient because it's invariant, and separates F1 modulo the group from F2 modulo the group, F0 modulo the group. Let's write this last statement cleanly and then go eat. Okay? I strongly recommend that you think about this. And if you want to write a little, I'm starting to give you little papers you can write. If you want to write a little paper around this subject of invariance, I would enjoy giving you more. I'll give you some more ideas. You can ask me for other ideas. Okay, let's write this cleanly. Here's the clean statement of what we just talked. Let's start with X as a topological space, T4 at least. T4. This should be a G space. Topological G space. I don't want to write too much. You have a quotient. G. This mapping is called pi. You have the continuous functions on x modulo g. You have the continuous functions on x. So far, so good. Quotient topology here, given topology there. You have the mapping pi. Pi pulls back a continuous function from downstairs. Pi is continuous. So it maps the continuous functions on x modulo g to the continuous functions upstairs. Clearly you take functions downstairs and lift them you don't get all functions, but what you get, trivially, is the invariant continuous functions. That's the definition, almost, of the quotient topology. You get the invariant continuous functions. In fact, I think you will be able to show this is very much an isomorphism. Isn't that beautiful? Pi is defined in such a way that it pulls back, it recognizes the continuous functions, the invariant functions downstairs as continuous, the functions downstairs as continuous invariant functions upstairs. Averaging maps, look at this. Averaging maps the continuous functions upstairs to invariant functions, so that maps to the continuous functions upstairs to invariant functions down to invariant functions upstairs. But invariant functions upstairs are the same thing as continuous functions downstairs. Okay? Please look at this tonight after you, don't drink too much wine. Think about this a little bit. You have a continuous map that in this T4 reasonable setting. You have the functions upstairs continuous, functions downstairs continuous. The mapping pi star pulls them back up. This is an isomorphism. These things that the averaging maps any continuous function to, I didn't prove it, but you can prove it, to an invariant continuous function, and we've just shown that that's the functions downstairs. Okay? Take two sets downstairs. Maybe I should call them something else. Tilde downstairs. Disjoints closed sets downstairs. Downstairs. Pi maps them to upstairs as disjoint closed sets. These are the corresponding closed sets upstairs. Upstairs, because continuous means pi inverse of a closed set is closed set, same as open. Upstairs. Take a function which restricts to 0 as 0, and it restricts to f1 as 1. You can do this because it's T4. Average this function. Restrict it to f0 tilde downstairs. This is a function. This is a function upstairs, but regarded downstairs because it's invariant, and that's an isomorphism. Downstairs. Check that this average function downstairs restricted to f0 tilde is 0, and this average function downstairs to f tilde 1 is 1. Now you're dead tired, and I'm a little bit tired too, but please look what we've done. There is a simple technology called averaging. It is a way of producing an invariant function from a function. Right. It produces functions downstairs that you can use. If you want to separate two closed sets downstairs, lift them upstairs, separate them by closed sets by functions upstairs. You use the function upstairs to separate this non-invariant, but you can average that function and make it invariant and therefore push it down. This technique is incredibly strong. Yes? Incredibly strong. This is the basic technique in invariant theory. And you see what it says. Maybe I should say, we win. We win. This technique says T4 upstairs implies T4 downstairs. And you will easily see Hausdorff upstairs upstairs implies Hausdorff downstairs. If some professional mathematician asks you, what do you learn from me? Tell him, we learned how to go back and forth from an arbitrary G space to the quotient of this G space, going back producing functions. If G is finite, look what the point is. There's exactly one point. The G is finite, right? You add up some numbers. Now I ask you, beginning students, I should ask you guys here, I won't put you on the spot, but I ask one of you guys, this guy from Uzbekistan. Yeah. If you're doing analysis, and somebody says, usually you sum over a finite set, and you make that finite set bigger and bigger and bigger, and maybe that finite set is really a continuum. You replace the finite set instead of a finite set with what? I'm terribly sorry. I'll say it again. If you make that finite set bigger, you make the finite set bigger and bigger and bigger, and you got sums and so on, and you take the limit of all this stuff, and you want to know what you get. What do you get if you're lucky? What's it called in analysis? -5 of 1610 to 20. Come on, we're all tired now. I make the group bigger and bigger and bigger and bigger and bigger. Maybe I'll let it approximate a continuum. Yeah? Make it bigger and bigger and bigger and bigger. What do you do, I'm sorry to put you on the spot, in analysis when you have a sum, and the sum gets bigger and bigger, and in fact, eventually it's sort of an infinite sum? How do you compute, what are you getting there usually?
G invariant integral, is that what?
Talk louder, Martin.
An integral over.
An integral.
Space.
That's the whole point of an integral. Right? Isn't that the point of an integral? Right? An integral, in the naive way you talk to some Mickey Mouse mathematician, it is an infinite sum. Or, yeah, it's an infinite sum. It's not an, yeah, it is somehow, right? But you have to make that precise. That means if you can find groups where this infinite sum converges, the averaging technique works. If you can find, and then what you would really like is to find uniform measure. Uniform measure and make this sum infinite. Uniform measure and make this sum, uniform probability distribution and make this sum infinite. Yes, here it is. Uniform, whatever that means, probability distribution, make this sum infinite. We need to understand we have this weighted sum. Of course, this goes to 0, but that's what you got to figure out what that means, and that's what Martin is saying. It's an integral of some sort, if you're lucky, right? Okay. So that was a big jump from the mathematics of the very early part of the 20th century to a little bit later, and this technique was taken into the technique for finite groups, where you add up things to bigger groups, which are called compact groups. And this method is very famous, and the people who quote it all the time don't understand it, so I demand that you understand it. Yeah? And this is called, in some section, Weil's trick. It is an example of an incredibly simple idea, averaging over the group, yeah, to produce invariant object on the quotient. Okay. I hope you can understand this. If you take my word that it's important, write a little paper on it. Submit this as part of your paper. Maybe I'll make some hints as what might be a good paper. called Weil's trick. It's not a trick. It's an obvious method. Okay. You know the name Hermann Weil, maybe. It was a German mathematician. That's okay. Thank you very much.